Now that we understand the history behind how parts of the atom were discovered, a little bit anyway, and we have a better understanding of where all of those parts are, now we can start to look more specifically at how many of the protons, neutrons, and electrons exist in atoms of different elements. So let's just make sure we have a good understanding of what a proton is. Rutherford finds the proton, right? And it's in the nucleus. He says it has a positive charge and it carries a mass. Since then, we have been told to assume that the atomic mass of one proton is 1 AMU. An AMU is an atomic mass unit. We can find out how many protons are in any element because the atomic number on the periodic table is the number of protons that is in the nucleus of an atom of that given element. Conveniently also, it's the number that organizes the periodic table. All elements are placed on the periodic table in order numerically according to their atomic number, which is the number of protons. Every atom of any given element has the same number of protons in its nucleus. So every hydrogen atom has 1 proton. Every helium has 2. Every carbon has 6, and so on. Whatever the atomic number is, that's how many protons it has in its nucleus. And every atom of that element has the exact same number. Neutrons that were discovered later by Chadwick are also massive particles. But these are particles that are in the nucleus that account for the mass. They are roughly the same size. So to make it simple, we're just going to say they are the same size in terms of mass as a proton, but they have no charge, so they are neutral. And then there are the electrons that J.J. Thomson found. Electrons, remember, are negative particles. They are found in the area outside of the nucleus. Remember, the quantum model now says we don't know the exact position of electrons, but we know they are in this sort of undefined area outside of the nucleus that we call the electron cloud. They have an extremely tiny mass, 0.0005 AMUs. Again, to make our life simple, we just get to ignore their mass. So when we are figuring out the mass number in a little while of any element, we will not deal with the electrons adding any mass. Now, the electrons are negative, the protons are positive, and since atoms are neutral, the positive and the negative have to balance each other out. So however many protons are found in the nucleus, that is how many electrons will be found in the electron cloud. So if you take a look at this example on the right-hand side, you can see essentially what the symbol for carbon looks like on the periodic table. Now, every periodic table is slightly different, but all basic periodic tables include some basic information that is the same. So they have a whole number, that counting number called the atomic number. Remember, that's the number of protons. And they also show the symbol here. The symbol for carbon, the letter that stands for carbon is a capital C. And they show as well the name and this, which is not a mass number, but is instead an average atomic mass. And we'll get to that in a few minutes. So how do we use the periodic table to figure out how many protons, neutrons, and electrons are in an atom of an element? Well, remember the atomic number is the number of protons. So that counting number, that whole number, is going to be the number of protons. For carbon, it's 6. The atomic number also gives us the number of electrons in a neutral atom. So the positive and the negative, when you add them together, add up to 0, which is what neutral is. So the atomic number also gives us the number of electrons. The protons and the neutrons are the particles in the atom that add up to give us the mass number. So if we want to find the mass number, we are going to add the protons and the neutrons together. If we want to find the neutrons, we are going to take the mass number, subtract away the number of protons, so subtract the atomic number, and we will have the neutrons. Now, from the periodic table, we cannot get the mass number because, as I already mentioned, this is not a mass number, it's an average atomic mass. The reason it's an average atomic mass is because not all elements exist exactly in the same way. Dalton said that they would, right? In his atomic theory, he said every atom of a given element are identical in all physical and chemical properties. But he didn't know about isotopes. Isotopes happen when atoms of the same element have a different number of neutrons. So they're the same element, therefore have the same number of protons, but they have a different number of neutrons. What that means is those atoms would have a different mass. So the number of neutrons of an element can vary, and that would give these atoms different atomic masses. This causes isotopes to vary in their physical properties, obviously their mass, but also it can have an effect on their chemical properties. Potassium, for example, has 3 different isotopes. Carbon has 3 different isotopes. Oxygen has 3 different isotopes. Hydrogen even has 3 different isotopes. The difference in having added neutrons can mean that they behave in different ways. It also often means that some of the isotopes will be radioactive. Now, because we have different isotopes that are the same element, we have to be able to distinguish between them. So we use a naming process. That naming process means that we're going to take the name of the element and we're going to include the mass number to specify the isotope. So for example, if we are talking specifically about the isotope of carbon that has a mass number of 12, we would name that isotope carbon 12. There is also a carbon with a mass number of 13, so carbon 13, and there is a mass of 14 for some carbon atoms, so we have carbon 14. Remember that the mass number is equal to the number of protons plus the number of neutrons. So all of these are carbon. When we looked at the periodic table, we saw that carbon had an atomic number of 6. So it has 6 protons. That means carbon 12, if we take the mass number of 12 and subtract the 6 protons, carbon 12 is an isotope of carbon that has 6 neutrons. Carbon 13, 13 minus 6 is 7. Carbon 13 has 7 neutrons. And carbon 14, using 14 minus the 6 protons, carbon 14 has 8 neutrons. We can also show this as a symbol. To do that, we use the symbol of the element as a large letter or pair of letters. On the upper left-hand side, we use the mass number that's given to us in the name. And on the lower left-hand side, we use the atomic number. So our carbon 12, carbon 13, and carbon 14 would look like this. All of them are carbon, so they all have the C. All of them are carbon, so they all have an atomic number of 6, but the different masses appear in the upper left-hand corner. So we have carbon 12, carbon 13, and carbon 14. We can also use a summarized diagram, sometimes called a Bohr diagram, to help us show what the electron arrangement might look like. Okay, so if we use potassium 39, the particular isotope of potassium with a mass of 39, we would look at the periodic table and find out that potassium has 19 protons. Because it has a mass number of 39, that means that it has 39 minus 19, or 20 neutrons. And neutral atoms then would also have 19 electrons. When we do a summarized diagram, we draw a circle in the middle to represent the nucleus. We put on it the symbol of the element. So for this, we have a K for potassium. We list the protons and the neutrons because those are the ones that are in the nucleus. So for potassium, we have 19 protons, 20 neutrons. And then we use dots in rings around the nucleus to represent the energy levels where the electrons are located. Now, this is called a Bohr model because it looks like orbits around the nucleus, like Bohr described them as. However, that's not what we currently think they behave like, but it is a good way to sort of diagram what it looks like. When you do these summarized diagrams, the very innermost ring, called the first energy level, cannot hold more than 2 electrons. So we will only ever put 2 dots on that first ring. Each of the rings, as you go out further, we're going to do a maximum of 8 dots. I personally like to organize my dots. It makes it easier to count how many I have. It's up to you whether you do that or not, but I think you will find it easier. So this particular diagram has 2 in the first ring. It has 8 in the next ring. It has 8 more in the third ring. So we have 2 plus 6 more, we have 8. Plus 8 more, we have 10, plus 8 more, we're up to 18, but a neutral atom would have 19, so we need that last energy level, and we need only 1 dot in that highest energy level. So we will draw as many dots as there are electrons, and we will have as many electrons as we have protons.